want to tell you about some of our work on the dynamics of pedestrian environment interactions, okay, and pedestrian interactions. So if we observe people behaving in an ordinary situation in a public space, we see patterns forming, right? So there are, in the Shibuya crossing here, there are large groups of people moving en masse in a collective motion pattern, lane formation observes, and so on. And so we think these global patterns are produced by local interactions happening at the individual level. So here's a street view of Shibuya crossing. This is what the local interactions look like, right? I'm walking across the intersection, avoiding other pedestrians, following some of my neighbors, and out of these local interactions you get that sort of global pattern formation. So what we're interested in working on is how, we want to understand how individuals visually guide their behavior. We're interested in what the visual input is of that street view and how that information gets used to generate individual behavior. But we can analyze behavior at multiple levels, right? So we're interested in individuals and how individuals guide locomotion, do obstacle avoidance. We're interested in collective crowd behavior, collective motion, and then ultimately navigation and wayfinding kind of beyond the sensory horizon of any individual and how we navigate a space that we can't actually see. So the goal is to build an agent-based model of how a pedestrian behaves ultimately based on visual information. So there are a lot of pedestrian models out there in the world, amazing numbers of them used for planning and design and so on. This is just an example graph from the web. Very few of these are actually grounded in experiments on human behavior, on how people actually behave and interact with their environments. So we're taking what I call a behavioral dynamics approach, very much inspired by the work of James Gibson on the perception of the environment and the control of action within the environment. He was a perceptual psychologist who founded a discipline called Ecological Psychology. Many of the talks I've heard today remind me of this. We're interested in the whole loop, right? And how you imagine, in this case, an individual agent coupled together with an environment. We think about this in terms of a dynamical system describing the environment, another dynamical system describing the agent, the couplings being how, for example, the actions of the agent change the state of the environment, and that then changes information available from the environment that then changes the state of the agent. And out of these sorts of interactions, right, you get emergent patterns of behavior, stable trajectories, for example, of somebody moving through a complicated space like this, where the behavior we see corresponds to kind of stable solutions of the dynamics of this entire interactive system, where the goal states correspond to attractors in the dynamics, avoided states correspond to repellers, and transitions between behavioral patterns correspond to, say, bifurcations in the dynamics. So the environment at this end, could be very simple, an individual obstacle that you're trying to avoid. It could be other agents, other pedestrians that you're interacting with and that are interacting with you, or complex architectural structures, right, that you have to navigate and get through. And I think of the world as following Gibson as kind of a set of affordances, right? That is, opportunities for actions of different kinds, and this term has come up in Sarah's talk and several other talks. So these are the opportunities for action that are presented by the environment, given your behavioral structure and your biomechanical structure. So in our case, we're interested in affordances for locomotion. Where can I walk? What do I have to avoid? What pathways are open to me in a building? Okay, so we study this using virtual reality. So this is the Virtual Environment Navigation Lab at Brown. It's just a big open room where people can walk around while wearing a wireless HMD. And we track their positions. We can do motion capture if we want to. And we can create various virtual environments to have people freely walk around in our experimental design. So simple environments with obstacles and goals, environments with virtual humans that we can prescribe their behavior, or more complex environments that have barriers and walls and structures. Okay, so let me start. I want to look at those three levels of analysis: the individual locomotion, the collective behavior, and then the problem of navigation very quickly. So starting with individual locomotion, one of our issues, and we were talking about this last night at dinner, is how do you decompose this problem, right, into a set of components that you might then be able to study and understand. So we just made a pass at this in terms of obstacles and goals. So an individual may need to steer toward a goal. It's got to avoid obstacles on the way. The goal might be moving, the obstacles might be moving. And there are other kinds of obstacles like extended barriers or walls that you need to navigate along. So there are a number of what you might think of as elementary behaviors that are going to be controlled by some sort of visual information, hopefully in a systematic way. So we started modeling each of these, just simple steering and obstacle avoidance, using a kind of mass spring metaphor, so model as second order systems, where the direction of travel of an individual moves as though they are attached by a damped spring to the direction of the goal. And so as the observer moves forward, their path is attracted into alignment with the goal, so there's a kind of a potential function there. If it's an obstacle, there's a potential hill that's pushing their direction of travel away from the goal. And so you can build up these sorts of models for each component of behavior that do a pretty good job of describing data that we collect in the lab. So here's the human data and the model performing it. Same thing for obstacle avoidance. We're now working on barrier avoidance, and how do you know which end of a barrier to go around? Wall following, again, pretty closely follows the human behavior. So we're kind of gradually building up these components of locomotion to generate a model that will then apply in more complex situations. So each component is nonlinear, but we can, the gamble is we can kind of linearly combine them in order to generate more complex behavior until that breaks, right? So you can do things like, here's our model avoiding multiple moving obstacles on the way to a goal, right? And it generates behavior that actually matches human performance quite closely. Okay, so now that's at the individual level. Now we want to think, if we understand how an individual behaves, maybe we can put them together to predict how crowds are going to behave, right? And then eventually we can think about those crowds moving within constraints like barriers and obstacles and walls. So at this point, we're now kind of saying, let's take this collective motion problem and try to break it down and look at the rules of engagement between a pair of pedestrians, and then what the neighborhood of interaction is for those pedestrian interactions. So in our more recent work, we've been looking at following behavior, so thinking that this might be the basis for collective motion. So we've been looking at how one person follows a leader when the leader might change speed. And so here's just a time series of the acceleration for the leader in blue, the follower in red. And the best fit model at this stage was a simple speed matching model that generated, the follower adopting the speed of the leader. And we're now working on a visual-based model that actually fits the human data better than this simple velocity matching model. Another problem is, for the following is how do you match the direction? If the leader changes direction, how do you respond to that? So again, looking at this empirically, the leader in red turns left, turns right. The human follower in black, does the same thing about a second later. And then the best fit model that we found is essentially a heading matching model, right? And so the follower kind of turns to match the direction of walking of the leader. And we now are working on a visual-based model for that as well. Okay, so now if we have this, this is how a pair of pedestrians interacts. What if I'm now in a group, right? And now we can take that group and simulate it in VR. So I'm now following a group of virtual humans. And as an experimentalist, I can now program the motions of those humans to test how my subject is going to behave. So I can make some of these virtual humans turn right, and others turn left, or some speed up and others slow down, and I can study what the responses of my human subject are. So based on data such as that, we derived, again, this is just a kind of an empirical description of our data, a simple sort of weighted average model, where the response of any individual to their neighbors is basically a weighted average of their neighbors' motions, where the weight decays exponentially with distance based on data that shows that indeed the coupling strength between me and my neighbors decays like this out to about 4 meters, and then I stop interacting right with my neighbors at that distance. And this sort of model we can then take and apply and simulate, see if we can simulate group data that we collect in the lab. So this is some human swarm data that we instructed people to just walk around together for 2 minutes right? But stay together. Liz is in here somewhere, in fact. And sometimes people follow leaders and sometimes they don't, right? So this leader now peeled off and nobody followed her. So there are interesting questions about what leadership means in a group like this. Can we understand how collective motion is influenced? Okay, so we could take this tracking data and then try to simulate it. So here's a sample simulation where we take the model and we can get kind of collective motion out of just the following model. So each of these simulated humans is following their neighbors according to our model. We can even go back into this data that we collected and try to simulate the trajectory of individual pedestrians, given that we know the input from their neighbors, right? So these are some chunks of data where an individual is in red, right? The model is in blue, and the model is taking input from all of the neighbors that were in that subject's field of view, okay, or that participant's field of view. And so time series of speed, time series of heading, we can get pretty good approximations. So we can, predict what an individual in a crowd is going to do based on the motions of their neighbors. All right, so we can now get more interesting, and we're just beginning to try to analyze and model this sort of data. So here's a counterflow case, two groups moving through each other, right? And you get this kind of nice lane formation, kind of like what we saw in Shibuya Crossing. So the blue and green form these alternating lanes, and it's a common observation. So we can now can we simulate that, right? If we have our two groups with driven by our model, two groups approaching each other, where they're now avoiding the oncoming pedestrians and following their neighbors. And again, you get the same sort of lane formation, right, out of those local interactions. The global organization seems to emerge. We're also doing some work on evacuation. So obviously one of the targets for this sort of modeling is, can we simulate how people are going to get out of a building? There are a number of companies around the world that are selling their services to architects who are building skyscrapers to try to simulate the evacuation times out of a skyscraper. But again, most of those models are not based on detailed understanding of human behavior, right? And so those things, these are baby steps here, right? That hopefully we can build up and introduce more and more complexity into the models. So we've done some things, some experiments using VR where we set up an evacuation scenario where a fire alarm goes off and then some virtual humans leave by one door and the subject actually came in the other door, and we can kind of play off the tendency to follow your neighbors toward one exit versus the tendency to go out the exit that you entered. And both of those tendencies we can actually show experimentally trade off against each other. So both of those tendencies influence people's evacuation behavior. So finally, let me just wrap up with navigation. And I think this is going to be talked about more by Mary and yesterday by Liz. But part of the question is, okay, now, so far I've been talking about things I can see, right? My neighbors, my obstacles, and so on. But I've got to often navigate to goals that I can't see, right? So what is my understanding of the environment so that I can navigate to a remote goal? So one of the questions we've been focused on is, what's the geometric structure of our spatial knowledge? There's a common view that we learn a cognitive map of our environment, where a map is thought of to be a kind of Euclidean structure where metric distances and directions are preserved. And the reason for thinking that is because that sort of knowledge would permit shortcutting behavior, right? Which is kind of the sine qua non of a cognitive map. It's like I can learn these locations and take a novel shortcut that I never took before. I can take novel detours that I've never taken before. So the problem with this view is that the data is really messy. The evidence for cognitive maps in animals and in humans is surprisingly weak. There's a lot of variability in human shortcutting behavior. But a Euclidean map is just at one end of a spectrum of possible spatial structures, right? Where the kind of the weaker end would be simple route knowledge, where I can only take routes I've learned, right, previously. There are intermediate structures like a graph, and someone mentioned Kevin Lynch's model of the Boston area in terms of nodes and edges. That would be a graph structure. And there's another labeled graph that has some local metric information, but that's not globally embedded into a cognitive map, right? So there's no, what a roboticist would say, there's no global metric embedding. So this local knowledge can be inconsistent, okay? And so we've done experiments where we try to teach people a complicated environment. This is kind of a hedge maze situation. And then we create a non-Euclidean version of that environment by inserting 2 wormholes in it. So if you walk down this path, the environment actually rotates and you pop out here in a different location, rotated by 90 degrees. When people, one group will learn this environment, another group will learn the wormhole environment. We train people in both cases from home to each location so that they have enough information to learn the Euclidean structure of the environment, but they also experience going through these wormholes. Then we ask people to do shortcuts, right? And so you start at one level, you take someone, say walk from home to point A, now I want you to walk directly, the maze disappears, and I want you to walk directly to point B. And in the Euclidean group, people can kind of do this on average because there's a huge amount of variability, right? But the constant error is only 3 degrees, right? So that's not bad, but the variable error is huge, okay? So we don't really know where B is. In the wormhole group, you take them from home to A, you say go to B, they go through the wormhole. They know where B is from that location, okay? And you take them from home to B, and you say go to A, and they go through the wormhole in the other direction. So you end up with, this is a reflection of spatial knowledge that doesn't satisfy the metric postulates. There are geometric inconsistencies in our spatial knowledge, and yet people can get around just fine, right, in this environment. Okay, and they're completely, the striking thing is they're completely unaware of any geometric inconsistencies after spending a couple of hours in this maze, right? So they're not integrating, right, into not into a global metric embedding. Okay, so let me just finish by saying, so hopefully, right, understanding how pedestrians move, navigate around, interact with other pedestrians, interact with the built environment, and somehow contribute to the design of more intelligent buildings. If we had a pedestrian model that was actually grounded in experimental data, right, in the way humans actually behave, we could then use that as a simulation tool, right, to simulate how people are going to react or respond or find their paths in different kinds of test environments. And we could use VR, ambulatory VR, to test those kinds of interactions in the buildings that we might want to construct, and a number of people have talked about that. Okay, sorry, I think I've run over, so I'm going to stop there.
Thank you.
Thank you so much.